Bismillahirrahmanirrahim. Hello and welcome to lecture number 2 of the course of Differential Geometry. Lecture number 1 में हमने यूक्लिडियन स्पेस की डेफिनेशन की थी. उसके बाद आफ्टर रिकॉलिंग द डेफिनेशन ऑफ फील्ड एंड वेक्टर स्पेस हमने ये देखा था हाउ यूक्लिडियन स्पेस इज अ वेक्टर स्पेस. उसके बाद हमने कुछ डिफरेंशिएबल फंक्शन की डेफिनेशन की थी और उसके बाद हमने एक्सरसाइज 1.1 से कुछ क्वेश्चंस किए थे. आज के लेक्चर में हम स्टार्ट लेंगे विद द डेफिनेशन ऑफ वेक्टर्स इन R3. हमने ऑलरेडी वेक्टर्स इन R3 की डेफिनेशन की हुई है, लेकिन आज हम देखेंगे हाउ वी कैन डिफाइन देम प्रिसाइजली so that we can use them efficiently in our course of differential geometry. उसके बाद हम टेंजेंट वेक्टर्स की डेफिनेशन पे जाएंगे. उसके बाद हम देखेंगे कि हमारे इर्द गिर्द बहुत सी एग्जांपल्स हैं वेक्टर फील्ड्स की और हम उनको मैथमेटिकली डिफाइन करेंगे. एंड इन ऑर्डर टू डील विद द वेक्टर फील्ड्स इन अ मोर एफिशिएंट वे वी डिफाइन नेचुरल फ्रेम फील्ड ऑन R3. और सेकेंड लास्ट स्टेप पे हम डिफरेंशिएबल वेक्टर फील्ड्स की डेफिनेशन करेंगे और हम ये रिक्वायर करेंगे कि आइंदा इस कोर्स में जब भी हम वेक्टर फील्ड्स लें वो डिफरेंशिएबल हों, क्योंकि हमारे काम के सिर्फ डिफरेंशिएबल वेक्टर फील्ड्स हैं, ऐसे वेक्टर फील्ड्स जिनको हम डिफरेंशिएट कर सकते हैं. उसके बाद एट द एंड हम एक्सरसाइज 1.2 के कुछ क्वेश्चंस सॉल्व करेंगे. जी, स्टार्टिंग विद द डेफिनेशन ऑफ वेक्टर्स इन R3. जैसा कि मैंने पहले कहा, वी हैव सीन वेक्टर्स इन R3 और आज तक जो हमने डेफिनेशन की है उसको मैं कहूँगा दिस वाज एन इंट्यूटिव डेफिनेशन. ए वेक्टर इन R3 इज एन ओरिएंटेड लाइन सेगमेंट. एक लाइन सेगमेंट है, तमाम इन्फिनिट लाइन नहीं, एक छोटा सा पार्ट लाइन का लाइन सेगमेंट, और इट्स एन ओरिएंटेड लाइन सेगमेंट. इसके ऊपर एक साइड में डायरेक्शन है. सो दिस इज वेक्टर. And we have seen that we can use these vectors to represent vector quantities. So what are the vector quantities? Vector quantities are those quantities which require magnitude as well as direction to completely define them. So for example, force vector. अगर किसी एक पॉइंट पे आप फोर्स अप्लाई कर रहे हैं तो जो एरो है उसकी लेंथ फोर्स के मैग्नीट्यूड को रिप्रेजेंट कर रही है और जो डायरेक्शन है एरो की वो ये रिप्रेजेंट कर रही है कि किस डायरेक्शन में फोर्स अप्लाई हो रही है. एंड वी नीड बोथ ऑफ दीज इंफॉर्मेशंस टू कंप्लीटली डिफाइन ए फोर्स. एंड सिमिलरली वेलोसिटी वेक्टर, उसकी जो लेंथ है एरो की वो वेलोसिटी वेक्टर के मैग्नीट्यूड या स्पीड को रिप्रेजेंट कर रही है और डायरेक्शन ये रिप्रेजेंट कर रही है कि किस डायरेक्शन में ऑब्जेक्ट मूव कर रहा है. And up to so on, there are many other examples like angular momentum and many more examples. लेकिन इस definition में क्या problem है? So definition की तरफ दोबारा जाते हैं. It's an oriented line segment, a line segment that has a direction. इस पिक्चर में आप देखें वेक्टर्स A, B और C तीनों की डायरेक्शन सेम है और इनका मैग्नीट्यूड या इनकी लेंथ वो भी सेम है. So by this definition, A is equal to B is equal to C. All of these three vectors must be equal. लेकिन प्रैक्टिकल लाइफ में आप देखें, फॉर एग्जांपल आपके पास एक लीवर है. लीवर के एक पॉइंट पे आप फोर्स F अप्लाई करते हैं और अगर आप सेम फोर्स, ए फोर्स दैट हैज द सेम मैग्नीट्यूड एंड सेम डायरेक्शन, आप किसी और पॉइंट पे अप्लाई करते हैं, you will get different results. So same vector gives you different results. So इस में एक problem है and we want to differentiate between these two force vectors. उसके लिए हम ये करते हैं, जिस पॉइंट पे फोर्स अप्लाई हो रही है या उसका जो इनिशियल पॉइंट है वेक्टर का, हम उसको भी इंक्लूड कर लेते हैं in the definition of the vector. So for example, in this case, this force F has initial point P and this force F has initial point Q. So we differentiate them like by saying this is P plus F and this is Q plus F. and that's how we define vectors in a more precise way. So a vector in R3 is P plus V, where P is the initial point and V is vector. So that's our precise definition of a vector in R3, जिसमें आप initial point भी लिख रहे हैं और vector भी लिख रहे हैं. Next हमारे पास है what is a tangent vector. A tangent vector to R3 consists of 2 points, its vector part and its point of application P. So for example, इस picture में आप देख सकते हैं this vector V that has P as point of application is a tangent vector to R3, और इस vector को हम denote कर रहे हैं with vector V underscore P. A tangent vector VP is drawn as an arrow from point P to the point P plus V. अब देखते हैं example में what does this actually mean? What does a tangent vector to R3 at a point, what does this mean? For example, आप point P ले लेते हैं 1 2. For example, आप point P ले लेते हैं 1 1 3 and आपके पास vector है 2 3 2. By definition, VP is equal to 2 3 2 subscript 1 1 3. This 1 1 3 is point of application or initial point of the vector. और इस पिक्चर में आप देख सकते हैं ये आपका जो पॉइंट है ये आपके पास पॉइंट ऑफ एप्लीकेशन है. और हाउ टू ऑब्टेन द एंड पॉइंट ऑफ दिस वेक्टर. वी नो व्हाट इज द इनिशियल पॉइंट ऑफ द वेक्टर 1 1 3. हाउ टू ऑब्टेन द एंड पॉइंट ऑफ दिस वेक्टर. एंड पॉइंट ऑफ द वेक्टर हम ऑब्टेन करते हैं बाय एडिंग P एंड V. अगर हम P और V को ऐड करें हमारे पास क्या आएगा. So for example, if we add 1 1 3 plus 2 3 2, x कोऑर्डिनेट को x कोऑर्डिनेट में ऐड कर लें. So 1 plus 2 1 plus 3 and 3 plus 2, which is equal to 3 4 and 5, and this is the end point of the vector. Initial point is 1 1 3, end point of the tangent vector is 3 4 and 5. So that is the example of a tangent vector to R3 at point P1 1 3. इसमें जैसा कि आप देख सकते हैं अगर मैं इस वेक्टर V को चेंज करूं तो बेसिकली ये जो tangent vector है इसका end point चेंज हो जाएगा, और अगर मैं P को चेंज करूं तो इसका initial point चेंज हो जाएगा. When two tangent vectors are equal and when they are parallel. So two tangent vectors VP and WQ. So this VP is a tangent vector that has initial point P, and WQ is a tangent vector that has initial point Q. So इसमें ये आपके पास point Q है और ये point P है. And they are parallel if W is equal to V. So for example, अगर आपके पास point of application different है इस केस में, लेकिन अगर आपके पास जो वेक्टर पार्ट है वो सेम है, then the two vectors are parallel. जैसा कि आप इस पिक्चर में देख सकते हैं, the vector parts are same but the initial points, the points of applications are different, but the vectors are parallel. Similarly, when we say that the two tangent vectors are equal, they are equal if and only if their vector parts are equal and their points of applications are equal. So both of them should be equal in order to the equality of tangent vectors. And similarly, if VP and VQ are different tangent vectors if P is not equal to Q. So in short, two tangent vectors are equal if and only if their vector parts are equal as well as their initial points are equal, or points of applications are equal. Tangent space. For any point P in R3, the set T underscore P of R3, or in short we can say that TP of R3 consists of all tangent vectors that have P as point of application and is called the tangent space of R3 at P. So for example, आपने उन तमाम वेक्टर्स को एक सेट में लिख लिया है that has P as their initial point. तमाम के तमाम vectors in R3 that has P as a point of application. Each point of R3 has its own tangent space. So if you change the point of application, you change the tangent space. क्योंकि जैसा कि हमने देखा है कि two vectors are different if their point of application is different. Even if their vector part is equal, but if their point of application is different, then they are different tangent vectors. So corresponding to each point of R3, we will have different tangent spaces, and they are different to each other because their points of applications are different. So we start with some recall from our previous maths courses. So given any two vectors in R3, we can add them by parallelogram law. So what is parallelogram law? The parallelogram law says that if you have a vector V and if you have a vector W, then you can translate V over here, and the vector joining the tail of the first vector to the head of the last vector will give you V plus W. So in short, by using parallelogram law, we can add two vectors in R3. So given two vectors in R3, I can add them. Similarly, if A is any vector in R3, I can multiply A by a scalar. What is the effect if I multiply a vector with a scalar? Either या आपका जो vector है वो length में बड़ा हो जाएगा, either it will stretch or it will shrink. This depends on the value of C. Also, it can also change its direction if C is negative. It can also change its direction if C is negative. So we can add two vectors, we can multiply a vector by a scalar. So under these two operations, we can in fact prove that R3 is a vector space. Now what's our next strategy? Basically, we want to borrow this way of adding and multiplying a vector by a scalar to the tangent space at any point. So given any two vectors VP and WP, both of them are tangent vectors at the point P, that's why they have the same subscript P, then we can in fact add them. VP plus WP is equal to V plus W subscript P. So in fact, if I want to add VP plus WP, which are two tangent vectors at point P, what I do? I just add the vector parts. So it's just जैसा कि हमने इस केस में देखा है, given any two vectors in R3, we can add them. और ये जो vector parts हैं दोनों tangent vectors के V plus W, इन दोनों को आप बिल्कुल using parallelogram law आप इनको add करेंगे, and then in fact you translate it to the point P so that its initial point or point of application is P. And similarly, we can borrow the scalar multiplication as well. So the effect of multiplying a tangent vector to a scalar C is basically CV into P, and once again this CP is the same thing as we multiply a vector by a scalar in R3, and then we translate it to the point P. So under these two operations हमने lecture 1 में vector space और field की definition की थी. So I won't go again to the definition of vector space. So we can see that this addition and scalar multiplication makes this tangent space at point P into a vector space under this addition and scalar multiplication we just defined. Next, we need the concept, or we need to recall the concept of a linear transformation. And why we need this concept? Because we want to find a relation between the tangent space at point P and with R3. And in fact, we will see that algebraically they are same, and there exists an isomorphism between them. So when I say algebraically they are same, it means there exists an isomorphism between them. And what is an isomorphism? Before that, we should go through the definition of a linear transformation. What is a linear transformation? If V is a vector space and W is a vector space, then a linear transformation is just a function from V to W which satisfies the following two conditions. So the first condition is it preserves the addition. So preserves addition means if I add two vectors and then apply the linear transformation, or if I apply the linear transformation separately and then I add them, then the effect is same, they are equal. So it preserves addition. And similarly, it preserves scalar multiplication, which again means if I apply L on the scalar multiple of the vector, it has the same effect of if I multiply the same scalar with the image of the vector under L. And if these two operations hold, if these two equalities hold, then we say that this function is a linear transformation. And I'm sure we have seen many examples of linear transformations. So for example, a function from R2 to R2 defined as xy goes to x plus y and y is a linear transformation from this vector space R2 to the vector space R2. And we can in fact find many other examples. And when this linear transformation is bijective, which means it is one-to-one and onto. And once again, we have seen the definition of what is one-to-one function and what is onto function in our lecture 1. So if a linear transformation is bijective, then we say that it's an isomorphism between the two vector spaces, and we call these two vector spaces to be isomorphic. And when we say that two vector spaces are isomorphic, it means that as a vector space they are equal. So if we just consider the vector space properties of V and W, then they are equal. So for example, in this case R2 is much more than a vector space, but if I just consider the vector space properties of these R2, then basically as a vector space they are same. So using this definition of linear transformation and isomorphism, we can prove that tangent space at any point, so P is any point of R3, and tangent space at point P is isomorphic to R3. And the isomorphism between them such that for any vector Vp of this tangent space, we define the image of Vp is equal to V. So we just consider the vector part of the tangent vector and we ignore the point of application. So if we consider this map, then under this map tangent space at point P and R3, they are isomorphic. And I'm going to leave this as an exercise for you, as an easy exercise for you, that this map defined above is basically an isomorphism. And then we can say that tangent space to R3 at any point is in fact isomorphic to R3. So the next concept is vector field. And before going into the mathematical precise definition of vector field, let me remind you that we have seen many vector fields. They are all around us. And the most important of them is gravitational vector field. So what does this gravitational vector field mean? So for example, if I have an object, let's say this green box, and it's resting on a 2-foot high table, then there is a force with which Earth attracts this box towards its center. And we can calculate the magnitude of the force by Newton's law of gravitation, but I won't go into the details. But what we can do is, we can represent this force vector by an arrow, and the length of the arrow represents the magnitude of the force, and the arrowhead or the orientation represents the direction in which the force has been applied. So it's always towards the center of the Earth. But what will happen if I move this object to 3-kilometer high point? Will Earth exert the same amount of force on the object? And we know that the answer to this question is no. The weight of the box is reduced. In other words, by Newton's law of gravitation, the force with which Earth attracts the body towards its center is reduced. So at this point, at 3-kilometer high point, if I represent the force vector with which Earth attracts the box towards its center with a vector, then the magnitude of the vector is now reduced as compared to when the box was on a table. So if I represent this force vector by an arrow, then the magnitude or the length of the arrow is now shortened, and then the direction is always towards the center of the Earth. And if I keep moving this box all around the planet, corresponding to every point, I will get a force vector. A vector whose magnitude represents the force with which Earth attracts the body towards its center, and the direction is basically towards the center of the Earth. And when you are close to the Earth, the arrows are bigger, and when you are away from the Earth, the arrows are smaller. And when you go very, very far, the arrows are very, very, very tiny. And similarly, and so we can associate a vector, an arrow, corresponding to every point around the planet Earth. So corresponding to every point in space, there is an arrow. And that's exactly what a vector field is. So a vector field is basically a function that assigns each point a vector. So in this case, this was the gravitational vector field that assigns each point around the space a vector. So precisely, how do we define a vector field? A vector field V on R3 is a function that assigns to each point P of R3 a tangent vector VP to R3 at point P. So mathematically speaking, it's just a function, and it's a function whose domain are the points of R3, and its range is basically set of vectors in R3. So give me any point and I will give you a vector at that point. So these are just two examples. So for example, at this point there is a vector, at this point there is a vector, at this point there is a vector. In fact, there are infinitely many points in space, but in this picture there are only finitely many arrows. So if we want to sketch all of them, then the picture will not be very clear. But in fact, there are arrows corresponding to each and every point in the space. So इसमें sketch तमाम vectors को इसलिए नहीं किया गया because the picture would be very difficult and very complex. And similarly, in the second example, this is a central object and there is some sort of force field around this object, and corresponding to every point around this particle there is a vector whose length represents the magnitude of the force with which this particle attracts the objects toward itself or away from itself. So in this case, away from itself, and in this case towards itself. Since a vector field is a function, so we can add two vector fields just like we add functions. And we have seen many examples of this, how to add two functions. And in fact, we have also seen this in our lecture number 1, that how to add two functions and how to multiply two functions. And since the vector field is a function, so we can multiply with any other real valued function. So if f is a real valued function on R3, then we can multiply f with v, and it's a function defined in the following way. If you apply this product on a point, then you just calculate the values point-wisely. So this is called the point-wise multiplication of the two functions. So in order to deal with vector fields more efficiently, or in order to understand their behavior in a more appropriate way, we introduce a set of 3 very simple vector fields. So investigate vector fields on R3, we introduced a set of basic vector fields on R3. So what is this set of vector fields? So this is U1, U2 and U3, and these are 3 vector fields on R3 which are defined in the following way. U1 of P, once again a vector field is a function. So if you want to define a function, one way you can define a function is define its image at each and every point at its domain. So U1 of P is equal to 1, 1, 0. So it's just a unit vector in x-axis direction, and you have translated this unit vector at the point P. So P is the point of application. And similarly, what is U2 of P? The second vector field. So you define this in the following way. U2 of P, the image of P under this function U2 or vector field U2 is 0, 1, 0, which is a unit vector in the y-axis direction, and you have translated this unit vector to the point P. And similarly, the third vector field is a function whose image at any point P is a unit vector in the z-axis direction, but you have translated this to point P. So for example, in this picture you have a unit vector in the x-axis direction or x1 direction, and if you just translate this vector to this point, so that the point of application or the initial point is point P, then this is the image of P under the vector field U1. And similarly, if you take a unit vector along y-axis or x2 axis, if you just translate this to the point P, then you will get the image of P under the vector field U2. And similarly for z or x3 axis. So in other words, if I change the point, I will get 3 mutually perpendicular vectors. So for example, if this point is Q, then I will get U2 of Q, U3 of Q and U1 of Q. And what is U1 of Q? So U1 of Q is basically, in this case, a unit vector in the x-axis direction and translated at point Q. And similarly, U2 of Q and U3 of Q. So the following result shows how to factorize, how to write down a given vector field as a linear combination of the natural frame. Okay, there is a lemma. If V is a vector field on R3, there are 3 uniquely determined real valued functions, V1, V2, V3 on R3, such that the vector field V can be written as a combination. Then vector field V can be written as a combination of U1, U2 and U3. So you multiply U1 with V1, multiply U2 with V2, multiply u3 with v3 and then add them, then it's the same as the vector field v. The functions v1, v2, v3, these are real valued function. They are giving you real numbers as an output, and these are called Euclidean coordinate functions of v. So in this picture you consider the image of the vector field at point P, and let's say it's this vector which is given in this picture. Then you can resolve this vector in the x-axis, y-axis and z-axis direction, and the components we can rename them as v1 of P, v2 of P and v3 of P. And we can do the same process for each and every point in R3, and for each and every point we will get these v1 of P, and if you change the point Q, then you will get v1 of Q, up to so on. So you get some image of each and every point of R3 under this function v1, and in fact these are real valued functions because their output is a real number. So let's have a look at the proof of this lemma. How can we say that? Do we have a proof? So by definition, the vector field v assigns to each point P a tangent vector v of P at P, and we have seen that in this picture. Why this is true? Thus the vector part of v of P depends on P because it's a function. Once again, let me remind you, a vector field is a function that has image values corresponding to each and every point in R3. So the image value of v under P is v of P, and it depends on P. So we write it down as v1 of P, v2 of P and v3 of P. So this defines v1, v2, v3 as real valued function on R3. So why this defines v1, v2, v3 as real valued functions on R3? Because these are functions such that their output is a real number and their input is any point in R3. So we can do the same procedure for each and every point of R3, and we will get corresponding to each point of R3 these values v1 of P, v2 of P, v3 of P. If you change the point to Q, then you will get v1 of Q, v2 of Q, v3 of Q. So we can get the image of each and every point of R3, and it's a real number. So we can say that we have functions v1, v2 and v3 such that their domain is R3 and their range is R. They are real valued functions. Their output is real. And if I want to calculate what is v1 of P, then basically I calculate what is the image of the point under the vector field, and this will give me as a first coordinate v1 of P, and similarly as a second coordinate it will give me v2 of P, and as a third coordinate it will give me v3 of P. So corresponding to each and every point I can calculate the images of v1, v2 and v3 at that point. So these are real valued functions defined on R3, or R3 is the domain of these real valued functions. So what is v of P? These are v1 of P, v2 of P and v3 of P translated at point P, or in other words P is the initial point. And why it's translated to P? Because the image of the vector field at any point P is a vector that has P at its initial point, or in other words it's a vector which is part of the tangent space at that point. And we can write this vector down in the following way, where v1 of P multiplied by this 1 0 0 vector but translated at P. Similarly v2 of P 0 1 0, v3 of P 0 0 1 of P, which is equal to v1 of P multiplied by u1 of P. This 1 0 0 is basically the image of the vector field u1 at point P, because it's translated, it's a unit vector in the x-axis direction translated at P, or we have made P as the initial point of this unit vector in the x-axis direction, so it's u1 of P. And similarly v2 of P multiplied by u2 of P and v3 of P multiplied by u3 of P. So the image of the vector field V, which was a very randomly chosen vector field, the image can be written as a combination of u1 of P, u2 of P and u3 of P. And these functions v1, v2, v3 are called the coordinate functions of V. So we can write down any vector field as a combination of elements of the natural frame field. And we will see that how can we simplify any situation by using this notation or by writing down any vector field as a combination of the elements of the natural frame field. So let me emphasize on the following two things. So the first thing is we use the following notation in the proof of the above lemma, Vi Ui, and we can see that the variable I equals 1 to 3 was not mentioned. It was not mentioned because we already know that we are in R3 and it's always going to be from 1 to 3. The variation of I is always going to be from 1 to 3 unless otherwise specifically mentioned. So this is equal to V1 U1, V2 U2, V3 U3. So as we have seen that we can add two functions, in other words we can add two vector fields, and we have also seen that we can write down a vector field as a combination of elements of natural frame field. So any vector field is basically of this form, Vi Ui, and any other vector field is basically of this form, Wi Ui, and we can add them in the following way by just adding the corresponding components. So V1 will be added to W1 and V2 will be added to W2. So in other words, Vi Ui sum Wi Ui is basically equal to V1 U1 plus V2 U2 plus V3 U3 plus W1 U1 plus W2 U2 plus W3 U3, and this is equal to V1 plus W1 U1. So we are just adding the first component to the first component and the second component to the second component. Sorry, this is V3 plus W3 U3. So that's what it is in the sigma notation or in the summation notation. And similarly we have also seen that I can multiply a vector field with a function. Vector field is also a function, but I can multiply this vector field with any real valued function. And in the same notation I can multiply vector field which is written as a combination of elements of the natural frame field in the following way. So I just multiply f with the components. So in other words, this is equal to f v1 u1 plus f v2 u2 and plus f v3 u3. And we will see, for example, in doing questions of the exercise, that these ways of writing down a vector field as a combination of natural frame field will hugely simplify the situation. Now, as said in the earlier part of my lecture, that we will always be interested in differentiable vector fields. Now what does a differentiable vector field means? So once again, writing down a vector field as a combination of natural frame field simplify the definition of what a differentiable vector field actually means. So vector field V is differentiable if each of its three Euclidean coordinate functions V1, V2, V3 is differentiable function. And we have seen the definition of what a differentiable function means, or what a C infinity function means. And if V1, V2, V3 are differentiable, then we say that this vector field V is differentiable. And we will not go into the definition of differentiable vector field in general, and we will just define them by writing down this vector field as a combination of the natural frame field. Both definitions are equivalent, but this definition is much simple, and we have made it simple by writing down a vector field as a combination of natural frame field. And from now onwards, we will always be interested in differentiable vector fields. And whenever I will be saying a vector field, it will always mean a differentiable vector field. In other words, the coordinate functions of the vector field are always differentiable. So for example, if V is a vector field, then I can write it down. That's just one example. So this is a vector field given as combination of U1, U2, U3, and in this case V1 is basically x square y, V2 is z, and V3 is x, y, z. So this vector field, which is written as a combination of U1, U2, U3, and we will always write down a vector field in the following way, which is much more simple way of writing down a vector field. And we know that polynomial functions, these are polynomial functions, the coefficients, and these are all differentiable functions at any point of R3. So this V is a differentiable vector field. So let's do an exercise. This is question number 1, part A of the exercise 1.2. Given a vector V which is -2, 1, -1, and another vector W which is 0, 1, 3, then at an arbitrary point P express the tangent vector 3VP minus 2WP as a linear combination of U1 of P, U2 of P, and U3 of P. So we are given V and W, and we want to write down this vector 3VP minus 2WP as a linear combination of U1 of P, U2 of P, and U3 of P. So we have seen that how to add two vectors in a tangent space. We have seen that we add them by borrowing the addition from vectors in R3. So in tangent space, all of the vectors have their initial point as point P, and we borrow the addition from R3 in the following way. We just add the vector parts and then translate the translated part to the point P. So let's just add these two vectors, and we know how to add the two vectors in R3. We just write down the vectors and add the corresponding components. So this is -6, 3, -3, -0, -2, +2, sorry, -6 at point P. So these are two vectors and I want to add them, so I just add the corresponding components. So -6 -0 is -6, and 3 -2 is 1, and -3 plus 6 is 3, and we translated them at point P. Now I can write this point as a linear combination of unit vectors. So -6, 1, 0, 0, minus 0 1 0 plus 3 0 0 1. And the whole vector is translated to the point P. So we can write down this vector in the following way now. This is just minus x u1 of p, because what is u1 of p? This is unit vector in the x-axis direction translated at point P. So this is 1 0 0 translated at point P, and similarly this is minus u2 of p, so unit vector in the y-axis direction translated at point P, and 3 multiplied by u3 of p. So we can write down any tangent vector as a linear combination of u1 of p, u2 of p, and u3 of p. And similarly we can do other questions of this exercise. And so in this case we have used this definitions. Next हमारे पास है exercise 1.2 का question number 2. So we are given two vector fields V, which is given as a combination of u1, u2 and u3, and here you can see that the coefficient of u3 is 0. And similarly another vector field, and it's given as a combination of u2, u3, and over here the coefficient of u1 is 0, and we want to compute this vector field w minus xp. And हम ऐसा क्यों कह सकते हैं कि w minus xp एक वेक्टर फील्ड ही होगा? क्योंकि हमें पता है अगर मैं किसी भी वेक्टर फील्ड को एक फंक्शन से मल्टीप्लाई करूं, वेक्टर फील्ड इटसेल्फ एक फंक्शन है, एक स्पेशल फंक्शन है, इसको मैं किसी भी जनरल रियल वैल्यूड फंक्शन से मल्टीप्लाई करूं, then it will again give me another vector field. And similarly when I add two vector fields it will give me another vector field. So इसका मतलब है w minus xp is a vector field, और इसको हम कंप्यूट करना चाह रहे हैं, in other words इसको हम लिखना चाह रहे हैं as a combination of u1, u2 and u3, और in other words हम इसके coordinate functions find out करना चाह रहे हैं, and then we will compute its value at the point p minus 1 0 2. So let's compute the vector field w minus xp. So we know w is given as 2x square u2 minus u3 minus x into v is given as x u1 plus y u2. So first हम इस चीज़ को compute करेंगे. What does it mean that we are multiplying x with this vector field? हमें पता है, हमने ये देखा है, अगर x कोई सा भी फंक्शन है इसको हम लीनियर कॉम्बिनेशन ऑफ u1, u2, u3 से मल्टीप्लाई करेंगे, then it will give me fv1 u1 plus fv2 u2 plus fv3 u3. in other words corresponding component से आप मल्टीप्लाई कर देते हैं. So इस चीज़ को हम as it is लिख रहे हैं. इस x को आप मल्टीप्लाई करेंगे with u1 coefficient and with u2 coefficient. So आपके पास बन जाएगा x square u1 plus x y u2. And now we have two vector fields and we are adding them. How to add two vector fields? We just add their corresponding components. So we are just adding their corresponding components. इसमें u1 का coefficient नहीं है और u1 का coefficient इस केस में given है. So this becomes minus x square u1, and what is the coefficient of u2? It's 2x square plus xy u2 and the coefficient of u3 is just -1. So this is the vector field W minus XV. So how to compute its value at any point? So we just compute its value -1, 0, 2. So if we want to compute the value of vector field at this point, it should give me another vector. It's basically once again applying one of these properties. So we just apply one of this property. So अगर किसी point पे v plus w का image हम find out कर रहे हैं तो हम v of p plus v of w करेंगे. So in other words, अगर 3 vector fields हैं तो minus x square u1 of -1, 0, 2 plus 2x square plus xy u2 applied on -1, 0, 2 minus u3 applied on -1, 0, 2. So what is the image of this vector field at point -1, 0, 2? So if you want to compute the image of the product of a vector field with a function f, so you just compute them separately at f and v. So what is the image of -1, 0, 2 at x square? So it becomes -1 square. And what's the image of -1, 0, 2 under this vector field u1? It's just 1, 0, 0 translated at -1, 0, 2 plus 2x square plus xy. Since y is 0, so this term is 0 and 2x square becomes 2, and the image of u2 at -1, 0, 2 becomes 0, 1, 0 at point -1, 0, 2. Minus 0, 0, 1, similarly -1, 0, 2. So it becomes -1, 1, 0, 0 at point -1, 0, 2 plus 2, 0, 1, 0 at point -1, 0, 2 and minus 0, 0, 1 at point -1, 0, 2, and we can collectively write them down as -1, 0, 0 plus 2, 0, 1, 0 minus 0, 0, 1 at point -1, 0, 2, and we can add these three vectors just the way we add them in R3. So it becomes -1, 0, 0 plus 0, 2, 0 minus 0, 0, 1 at point -1, 0, 2. So this becomes -1 plus 0 minus 0 is -1, 0 plus 2 minus 0 is 2, 0 plus 0 minus 1 is -1 at point -1, 0, 2. So this is the image of W minus XV at point -1, 0, 2. And similarly, we can solve other exercises from the book. Next time, we'll be interested in directional derivatives. So in this lecture, what we have done so far. So starting from a precise definition of vectors in R3, we define after that what is a tangent vector to R3 at a point. And then at any fixed point, the collection of all vectors with P at its point of application, we define the tangent space at a point. And then after that we proved some properties about this tangent space, that if we consider only the vector space properties of this tangent space, then this is isomorphic to R3. So in other words, tangent space at any point of R3 is basically, as a vector space, is the same as R3. They are isomorphic. And next we define what is a vector field, and more importantly, why do we need the concept of vector field? Because we have seen many examples of vector fields, and then we defined vector field in a more mathematically precise way. It's just a function. And then we write down a given vector field as a combination of more simple vector fields, and we have seen that it's very simple. It's very simple to use that combination while solving problems. And then after that we did some exercises from the exercise 1.2. This is the end of the lecture. Thank you very much.